going to look at a more complicated recording. And let me open the EVA Analysis Tools software. And I'll select this recording. And I'd like, just looking at this, right, what we see is that the z-axis or the vertical axis motion is the dominant issue here. Right? I'm going to pass it through the human response filter. And now we look at this in comparison. There's really not much happening on the x-axis. ISO y-axis pretty low. But look at the vertical axis. The maximum is 43 or almost 44 compared to the x and the y, significantly worse. The A95 is, and think of the A95 as a typical vibration. These vertical dashed lines mark 0.5 meters from the beginning of the recording, or from the beginning of motion, and 0.5 meters from the end of motion. So within the ISO standard, we evaluate ride quality between those 2 points in travel. And I'm going to zoom in on well, not quite yet. I'm going to use a tool called the FFT, which stands for Fast Fourier Transform, and just think of it as vibration versus frequency. So I'm going to pick my starting point where the car is moving at full speed. So somewhere in here I'm just picking where we've reached full speed. Because if you're talking about a rotating element, then if you're talking while speed is changing, then the frequency of that rotation would change. So here we're looking at where everything is relatively constant. So I'm going to do FFT, and I'm going to z-axis, 4-second length, and OK. And let me just pull it down. So this is the area in which I'm evaluating. And you'll see, and what you'll see here is this is a segment that I'm evaluating, and this is vibration level for each frequency. And you'll see the biggest one here is somewhere around 26 hertz. So we see something here about 4.5 hertz, about 26 hertz, about 52 hertz. And often this will, when you see anything, sometimes you'll often look for a harmonic. So 2 times 26 is 52, times 3 is 76, or whatever it is. Right? That's the idea. That's the way you actually start attacking this. But what I'm going to do, we think about this. So the consultant at the time was thinking, this is somehow related to ropes, right? If it were a rope-related issue, then what you should see is a change in frequency. And think of a guitar string as it gets shorter and shorter, right? You get a higher and higher pitch. But you should see a change in frequency as we travel up the hoistway. So here we're seeing that the dominant one is 26. And it's a fairly complicated thing, so there's other things happening in there as well. I'm going to move further up the hoistway, about halfway up, and do the FFT again. Z-axis, 4 seconds. Right? And now it's starting to look more and more like a very clean sinusoid. And 26 hertz is still the dominant thing, but it's just getting much taller than everything else. Where before it was less than half of this, now it's up to about 7.5 at just that frequency. I'm going to close this, and I'm going to move up the hoistway again. I'll do the same thing. And it's now a pure sinusoid. Where it was 7, it is now up to 15 almost at just that one frequency. So the frequency did not change from bottom of the hoistway to the top of the hoistway. In general, as you get closer to the source of vibration, the vibration level increases. The frequency did not change, so we're going to say, okay, ropes are not a related issue here. This is just, we're getting closer to the source. If it were, let's say, a main drive sheave problem, right? The main drive sheave for 900 millimeters, this is something you would enter, rotational frequency is about 0.6, and that would be all the way down here. But in fact, this was a geared elevator, and the motor RPM was 1550 RPMs, which is what I entered right here, and I'm just going to show it. And you'll see how it matches pretty precisely, right? So what it's saying is that the gearbox is actually the vibration source of this signal, because it's tied directly to the motor RPM. There is a match. So when you're using the FFT, you're looking for matches. If we were dealing with guide rollers, we would do an FFT of, let's say, the X or the Y axis, one of the horizontal axes. We'd put in the guide roller diameter, and we'd follow the same type of approach. But in this case, we're doing a vertical vibration. It's not related to any of the rotating elements, but let's think of what those rotating elements would be. So there would be the sheave, the secondary sheave, the counterweight guide rollers. All of those are rotating elements that are going in. But in this case, we have a geared elevator, which is several rotating elements within there. So we have a motor turning a worm, turning the wheel, right? So all of these have their own frequencies. Now, in this case, the motor RPM and the worm are turning at exactly the same RPMs. So this is related to the gear mesh, and specifically, what we did was we went up into the machine room, measured the vibration directly on the gearbox. We got exactly the same thing that we're seeing in the car. So it's important to keep in mind that what you measure in the car is a summation of everything that's happening in the system, right? We're looking at either for horizontal sources or vertical sources. In this case, the vertical source was a gearbox. It's a good way to identify where the problems are, and we can just simply do it by measuring on the floor of the car. All right, I hope this was helpful. If you have any questions, please let us know, and we will try to do everything that we can.